So the story of mathematics begins a long time ago. And it really begins with humans collecting together bits of information that they found useful, an odd assortment of curios, if you will. Now, as the curiosity and natural inquisitive nature of humans took over, this wealth of knowledge began to grow and take shape. A pivotal time in the history of mathematics, and indeed the sciences, was when Euclid arrived. This was about 300 BC, and Euclid today is famous for writing a series of 13 books, which we know as the Elements. In these 13 books, he collects together a large proportion of the amount of knowledge in mathematics at the time. You could think of the Elements as the Wikipedia for ancient Greek mathematics. Now, these have been arguably called the most successful and influential textbooks of all history. In fact, they're estimated to be the most published book apart from the Bible. Now, it's not actually what is true in mathematics that we learn from Euclid, but why something is true in mathematics. You see, let me explain it in this way. Let's say I give you a maths problem, and I know you didn't come here for that, but say you wanted to show that a triangle with 3 equal side lengths also has 3 equal angles. How would you do it? Well, we mathematicians usually take a complicated statement like that and try to break it down into smaller pieces. Those smaller pieces are then reconstructed using logic to explain the more complicated fact. But this begs the question, how do you know that those smaller facts are actually true? Well, you repeat the process. You say, can I break those smaller pieces into simpler pieces still? But where does it all end? How do we know that we're not caught in some infinite regress of just ever increasingly simple facts? And if that's all we mathematicians did, just look at simpler and simpler facts, then it would be a pretty boring game. And let me tell you, mathematics is interesting. I hope you'll agree. Okay, so what Euclid did was to turn the whole game of mathematics on its head. He said, instead of taking a complicated fact and trying to break it down, let's start from the bottom. Let's use the reductionist approach. He enunciated some basic building blocks, some very, very simple facts in mathematics, from which he would then try and deduce everything that was known at the time. In the world of geometry, Euclid started off with 5 of these basic facts, which he called axioms. I call them Euclid's pencil case. Here's a picture of 4 of them. And these are so basic, they're irrefutable essentially. Everyone has to agree that they're true. And if you agree with Euclid's axioms, then you must necessarily agree with everything Euclid deduces. So the first axiom is very simple. It says that Euclid said, I have a ruler. If you give me 2 points, I can join them by a line segment. Okay, there's not much happening there. The next axiom is that, well, not only do I have a ruler, I've got a longer ruler. If you give me 2 points, not only can I join them, I can extend that line in both directions. Euclid's third axiom, there's such thing as a set square. I have one of these in my pencil case. What it means is that right angles are always the same. If you have a right angle in your pocket and I have a right angle in my pocket, we can always line them up so they look exactly the same. And the fourth axiom just says that we can draw circles. Give me some centre and some radius and I can swing that compass around and draw a circle. Where things start to get more complicated is when it comes to Euclid's 5th axiom. This is called the parallel postulate. And it's complicated because it doesn't correspond to something you carry around in your pencil case. What Euclid said is that if you give Euclid a line and some point, he said that he can always find a line through that point parallel to the original that doesn't touch the original. So, mathematicians observed then, and I think you'll observe now, that this 5th axiom is actually much more complicated than the previous 4. In fact, mathematicians wondered, can we do away with it completely? Could we not include it in our list of atomic facts, in our list of axioms? And could we actually prove it from the other 4? So the challenge was set for mathematicians, and many mathematicians through the ages tried and failed to prove this complicated parallel postulate from the preceding 4 axioms. And it wasn't until the 19th century, over 2 millennia after the time of Euclid, that the puzzle was resolved. It turns out that we can't actually prove this complicated postulate from the other 4 axioms. And the general reason is as follows. Because Euclid's geometry is not the only game in town. There are many flavours or versions of geometry, and in some of them, this parallel postulate isn't true. And in fact, one flavour of this geometry should be very familiar to you. It's the geometry of the Earth, of the sphere. The parallel postulate doesn't hold here because parallel lines don't even exist. One way to think about it is that if you have two planes flying in straight lines over the Earth, then those flight paths are always going to cross sooner or later. So we even know now from Einstein's theory of general relativity that the space we inhabit, the universe, doesn't obey Euclid's rules. Even though, say, drawings that you might draw on a piece of paper, or architectural plans, or other geometric figures on our worldly scale appear Euclidean to us, physics dictates that on large scales or near massive objects, that's just not the case. So in some sense, we could say that Euclid was a little bit wrong, as amazing as he was. So I'd like to leave Euclid behind and jump to another period in mathematical history. Now, mathematical history is intricately tied to the history of the sciences. You can think of science as being this process of observing phenomena in nature, then measuring those phenomena and trying to explain what you see. It's a fundamental question to ask, how do you measure stuff? I'd like to break it down and think about a simpler question. How would we measure the area of Australia? So it turns out that mathematicians have actually not come a long way in terms of measurement. We do it the same way that you might have learnt in primary school. What you would do is you'd draw the map of Australia on a grid of squares and you'd start counting. Now, we all know Australia's not some pixelated country made up out of squares. There are inny bits and outy bits and wiggly bits. So you have to count parts of squares. But how much of that part do you count? So a way forward is to actually not try and get the exact area, but to think about estimating the area. How does this grid of squares help us? Well, we can get an underestimate. That's pretty easy. You just count those squares that lie completely within the map. On the other hand, you can always get an overestimate as well. Don't just count those squares that lie inside, but count those squares around the edges, which just touch the map. This is not particularly satisfying because we've got this underestimate over here, this overestimate over here, and your answer could be any of these numbers in between. But what we do now is we just play the game again using a smaller grid of squares. What you'll find is that you'll get a better underestimate and a better overestimate, but still you haven't honed in on your answer. So what do? You play the game again and again and again, infinitely often, and sooner or later those over and underestimates will sandwich in the correct answer. Now, to a mathematician, this is thoroughly unsatisfying. Why, when you want to measure the area of a shape, do you need to do something infinitely often? Who's got that sort of time? So a way around it was proposed, a way to try and compare the area of two different shapes without using some infinite procedure came about. And the method is this. It's clear that for a shape, in terms of its area, a shape is always the sum of its parts. If you can cut it up into pieces, then the area of the original matches the sum of the areas of those little pieces. So if I give you two shapes, and you can cut one using scissors and rearrange those shapes to make the other, then those two shapes that you started with have to have the same area. Let's see an example. So this is just a square and an equilateral triangle of the same area, and you can see from this picture that the square can be cut into 4 pieces which rearrange to make that triangle. And actually, it was proven by mathematicians that this is true for any two shapes you begin with the same area, as long as they're made out of straight edges. You can always cut one using straight lines into a bunch of puzzle pieces, rearrange them to get the other, thereby proving that they have the same area without resorting to some infinite procedure. It turns out that this mathematical theory of measurements has a lot of counterintuitive and rather amazing facts. So let me tell you about a couple more. You see, we could have, instead of asking for the area of Australia, asked for the length of its coastline. And if I asked you that question, I'm sure what you'd do is you'd pull out your phone and look it up on Wikipedia. And what you'd find is that the answer, according to Wikipedia, is 25,760 kilometres. That's all well and good. But actually, if you read Wikipedia a little bit more, it also says that the coastline of Australia has the length 66,530 kilometres. What's going on, Wikipedia? These two answers are completely disparate. So it turns out that measuring the coastline of a country is a much more mathematically subtle issue than you might at first suspect. Because it all comes down to the fact that these coastlines are incredibly wiggly. In mathematics, we'd say that they exhibit fractal behaviour. So, trying to measure the length of a coastline actually comes down to how you do it. If you use a shorter ruler, you'll pick up more of the wiggles in the coastline, and hence you'll get a longer answer. So I'd like to jump to another point in mathematical history. I'd like to tell you about another field of mathematics in particular. The field of mathematics is something that's very near and dear to my heart, what I do research in. It's called topology. And now you can think of topology as geometry's wacky cousin. Like geometry, topology studies shapes. But in topology, we play by a very different set of rules. You see, in topology, we're allowed to take a shape, and we're allowed to bend it, stretch it, squish it, flex it, squash it, and still consider it to be the same. So for instance, I could take a square and take a circle, and in the eyes of a topologist, these are exactly the same. The reason being that you take that square and you start padding in the corners, you start rounding it out, and sooner or later, you end up with a circle. In fact, I could have started with a triangle or a hexagon or something like that, and still ended up with a circle. So in the eyes of a topologist, squares, circles, triangles, these are all boring. We don't care about them so much. Where things start to get interesting is when you think about surfaces. To understand what a surface is, pretend you're this little ant and you're crawling around. And everywhere you crawl around, you notice you're surrounded by this little patch of land, just like I am right now. Well, what surface could you be on? Humans were confronted with this very same problem thousands of years ago. Humans realised that wherever you walked or sailed, you were always surrounded by this little patch of earth around you. And humans therefore decided, rather naively, that we're probably living on some infinite expanse of land that stretched us infinitely far in every direction. Now we know that that's not the case. As previously discussed, we live on a sphere. So if you're this little ant walking around, you might also be living on a sphere. But what other options are there? It turns out that you could actually be living on, say, a donut, or even a two-hole donut, or something much more mathematically crazy still. To give you more of the flavour of topology, I want to take you back many years to a computer game called Pac-Man. And some of you, I can see, are too young to know what this game is about. It's okay. All you need to know is that Pac-Man's universe, Pac-Man's world, is your computer screen, your rectangular computer screen. But with one interesting feature. When Pac-Man goes off one side of the screen, he comes back on the other side. Let's suppose also that when Pac-Man goes off the top of the screen, he comes up through the bottom. What we observe now is that Pac-Man lives on a surface. Everywhere he stands, he's always surrounded by a little two-dimensional patch of land. He never runs into any boundaries. He doesn't see the side of the screen. He just goes straight through it and comes in the other side. So the question we'd like to ask and answer is, what surface does Pac-Man live on? And this is how a topologist would solve this problem. You see, let's concentrate on the edges of the screen. In particular, look at that top edge and the bottom edge. Remember, when Pac-Man goes up the top, he comes in through the bottom. To Pac-Man, he doesn't know the difference between the top edge and the bottom edge. To Pac-Man, they're the same thing. And if they're the same thing, let's put them in the same place. We're going to roll up our computer screen and glue that top edge to the bottom edge. Don't try this at home. Of course, in topology, though, we're allowed to bend and flex and stretch and squish our shapes. And this is what you'll see. You'll see that the shape that you obtain is what a mathematician might call a cylinder, and you might call a toilet paper roll. Similarly, though, to Pac-Man, he doesn't see the left and right edges of the toilet paper roll. He just goes straight through them and comes back in the other side. So, we should do what we did before and take those two ends and glue them together. And the picture we obtain is the following. You recognise this, of course, as the surface of a donut. And so, hopefully, if you learned something new today, you've learned that Pac-Man lives on a donut. We're going to shift gears now. Surfaces, in some sense, are two-dimensional. An ant can walk around on them. Let's consider now an ant flying around in a spaceship. And let's suppose that our ant is in this universe where everywhere it's flying around, it notices this three-dimensional blob of space around it. In some sense, this is a three-dimensional analogue of a surface, and we mathematicians call these objects three manifolds. Now, the same questions remain. What sort of universe could an ant be living in? Naively, you might think that the universe then expands infinitely far in every direction. But that would be falling into the same trap as our human ancestors who thought that the world was flat. Because it could actually be that the universe that our ant lives in, indeed the universe that we live in, is much more complicated than that. It could be, just as you can sail around the Earth and come back to where you started, it could be that if you travelled far enough in a particular direction, you actually came back to Earth. It could be that the universe that we live in is actually a three-dimensional analogue of a sphere. Or indeed, we may be living in a three-dimensional analogue of a donut, or something much crazier still. Whereas physicists have yet to understand exactly the shape of the universe that we live in, though, mathematicians aren't so constrained by reality. In mathematics, we explore all of these universes, and this theory of three manifolds has continued with breakthroughs happening all the time to this day. So what we've seen today is a few different sections in the history of geometry. We learnt about Euclid, what he told us about mathematical truth. We've seen how the theory of measurement from the mathematical viewpoint can come up with quite thorny and counterintuitive issues. And we've seen how in mathematics we're allowed to change the rules, bend the rules, and bend our shapes. So these are just some key chapters in the story of geometry. The story of geometry plays a very important role in the story of mathematics more generally. And, at least in my opinion, the story of mathematics plays a crucial role in the greater story of humankind's quest for knowledge. Thank you.